Did your girlfriend leave you? Does your dog urinate in your bed? Well, today you're going to win her back and you're going to win the respect of your dog because today you are going to make an 8x8 scroll text for the Commodore 64. Let's get right into it. We're going to start with star equals 0801. This is the start of Commodore Basic. And we are going to begin by putting some bytes into memory. I will be using C64 Studio. I've been using this for about the last couple of weeks. You can download it. There will be a link in the video description. If we want to put bytes into memory, we use the exclamation byte command, and we just put them in hex or decimal format. So I'm going to be putting 080B, which is going to be the link to the next line of basic. And then exclamation mark byte 00, which indicates the line number. So you can change that if you want to play with the line number. You can change the low address or the high address. If you put both to FF, then you get 65535 for a line number. You can change it to something like 2026, whatever you prefer. And then next we have 9E, which is the token for SYS. And then we have 4 bytes, which are numeric, 32, 30, 36, and 31, which corresponds to 2061. And then we terminate with 3 zeros. What this does is, let me just compile it. I'm expecting it to crash. That's okay. 080B is the pointer to the next line number. It's used when you're writing a basic program, but because we're just making a single line program, it's going to point to 2 zeros, indicating it's the end of basic. There's no more basic program. 9E will put an SYS command, and then it will put 2061, and then, of course, the 3 zeros to terminate the program. I'll put RTS, which means return from subroutine. It's just going to kick it back to basic. And if you list, you have 02061. I'm using the CCS64 emulator. If we go into memory using Alt-M, you can see the bytes in memory. 0800 has a 0 always. Here's the 0B08, and then the line number pointers I was telling you about. If we change those 2 zeros to FF, then the line number becomes 65535. You take the low byte, and then the high byte is divided by, or is multiplied by 256. So if you want to do something like 666, that is 666 minus 512. So it's going to be 154 and 2. So we can go in and we can change to 154, 2. I just removed the $sign because it's no longer hex. And then I compile it. To compile, you press Control F5, I believe. 666. How evil. Yeah, Control F5, or you go up. I don't think the screen capture shows this little window, but if you go up to build, it's build and run. So we've compiled what we call a basic stub. It's just a single line number, 10 SYS 2061. And given that it's going at 0801, which is 2049, this is 2049, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, and the SYS number is 2061. So this is the first address to get executed. Let's get right into it. We're going to load A with 0. This puts a value of 0 in the A register. And then we're going to store A in D020, D021, which is the border and screen registers. The next step is we're going to clear the screen by loading A with 93, which is the PETSCI symbol 147, also known as the clear screen. JSR FFD2 is a built-in kernel routine which prints whatever is in the A register. So since we've put 93 into A and called FFD2, it's now going to clear the screen. We're recycling A. We've used it for the border, and then we are using it to clear the screen. I will compile it, and it should change the screen to black, and it has cleared the screen. Perfect. All right, now the next thing we're going to do is we're going to set up a couple of variables, and I will do that right here. So we're going to have scroll text. In order to do that, we have to define the location of our scroll text. So you're going to load A with number less than TX, which is going to be short for text, and start in BB. You're going to load A with number greater than TX and store that in BC. And if you've been watching my videos, and I hope that you have, you'll know that using the less than and greater sign sets it up for the low byte and the high byte, because every location in the 64 has a low and a high byte. If you want to call, say, C1000, which is 49152, well, C1000 is the low byte, and then the high byte is C0. The high byte goes first. So the computer knows where a scroll text is. We have to give it the low and high byte. And we haven't defined TX yet. So you're going to go scroll down. And C64 Studio is case sensitive. So we can't use lowercase in one spot and then uppercase in another. They have to match. And we're going to put exclamation mark SCR, which is short for screen, I think it's screen text. It just puts in memory, rather than PETSCI, it puts in the proper numerical values, like A equals 1, B equals 2, instead of A being 65, which is PETSCI. So TX, exclamation mark, SCR. We'll start with a space. And this is my new 8x8 scroller. Show this to your former girlfriend, you will win her back. And then I'm going to terminate it with a exclamation mark byte 0, so that it knows when you're finished the scroll text, when it's time to wrap, when it sees a 0. We're going to load A with 0 and store A in column. And we have to define column. Can go before or after your scroll text. It does not matter. Exclamation mark byte 0. And then we'll run the code. So if we look at location BB and BC, it points to 0828. If we look at 0828, it is our scroll text. How did it do that? It did that because in the code where we put number less than, it filled in 28 for us. And where we put number greater than, it filled in 08, which points to 0828. That is the low and high byte. This is the low, 28. and 08 is high. So it does the work for you. And then 853 is going to be the location of our variable column. You can see in the far left-hand column, it tells you where the addresses are, where they go in memory. And I'm going to take you away for a second, and we're going to load a program called 99 character sets. It will be included. Turn off the sound. All right. So I have to turn on the joystick. And this is exactly as the name says it is. 99 different character sets. You can pick whichever one you prefer. There's almost 100 of them. I'm not sure if there's a save in here or not. I don't think there is. So what you're going to need to do is either have a cartridge on your real 64 or go into the monitor using Alt-M as in Mary or Alt-H as in Harry if you're using the Vice emulator, or go up to the menu and select Machine Language Monitor. So we're going to go Alt-M, and whatever character set you pick is in 2000 hex. So if you type M2000, you should see some sort of it almost looks like a grid pattern, but this is, you come to know it as a character set. After you've seen 100 of them, you realize that it's a character set. So using the monitor, I'm going to save it. I'm going to call it 2000 char set, 2000 space 2200. I'm only going to be using A to Z and the numbers and the graphic symbols. I'm not going to be using shifted characters or anything fancy. So even though the character set goes up to, I believe, 2800, we only need the first two rows. So I'm going to save from 2000 to 2200. If you're using a different monitor, like one in a cartridge or in Vice, you'll go save 2000 char set. And then 08 for drive 8, 2000, 2200. And if that does not work, because you're using a real monitor on the 64, try putting commas. Comma 08, comma 2000, comma 2200. In the end, you should have a file that is named 2000 char set. I'm just going to dig around my drive and see if I can find that. So now that you have your character set picked out and you've saved it to disk, it'll have to be in the same folder as the program that we're making. And the first, I skipped over that step, I'm sorry. In C64 Studio, you'll go File, New, ASM file, because you want to make an assembly file, and then type in the code that I have given you. So star equals 0801, your byte 0B08, and then 00, comma 00 for the line number, 9E, 32, 30, 36, 31, 3 zeros. And then we're setting DO20, DO21 to 0. Loading A with 93 hex, JSR FFD2. And we're setting the low and high byte of TX, storing it in BBBC, which is a safe zero page location. And then when you go File, Save As, I'm putting it in the directory is called WizBall, but it's not WizBall. So that is it so far. We just have our scroll text pointer, and we've defined a column. And now what I'm going to do is load in a program called Ultrafont. because I want to show you how a character set works. I've already presented 2 videos that use custom character sets. So I believe it was 2000 char set 7000. And this is the character set I will be using. You'll see that the characters are made up of 8 pixels across and 8 pixels high. So there are 64 pixels altogether in every Commodore PET character, which is not unsurprising because there are 40 characters across the screen, and 8 times 4 is 32, so it's 320 by 200 resolution. 25 rows, 25 times 8, 200. So you get a 320 resolution using an 8 by 8 character set. So in the last video I kind of broke down how characters are saved in memory. And for this video, you're going to have to know a little bit about how that works. So the way it works is the character set is stored in rows. It does not go up and down, it goes across. So say, for example, this character set is the one that you saved from the 99 character set program at 2000. Well, the first character is not being used. So this is 2000, 2001, 2, 3, 4, 5, 6, 7. This is 2008. Now, because this character set loads in at 7000, just temporarily I'm going to show you at 7008. You'll see the first line is a 0 because there are no pixels turned on. And then, so there's nothing there. And then we have pixels 1, 2, 4, 8, and 16 are turned on. So 8 and 16 are turned on. If we look at 7008, you'll see a value of 18, which is 24. So 8 plus 16. Or if you want to break it down as far as hex goes, it's 8 and 10. I'll put that up on the screen so you can see it. But basically, every character set, every line of the character set takes up one memory location. In the final product of your 8 by 8 scroll, this will be 2008, 2009, 2000 A, B, C, D, E, F, and then the top of B will be 2010, and so forth. How does it work as far as the pixels go? Well, the pixels are either turned on or turned off. And depending on which ones are on, which ones are off, defines what value goes into the location. I'll give you another example. Let's say we have 7000. I'm going to put an FF, a 01, and an 80. And you see the first line becomes all turned on bits, which is FF. And then the first bit is on, which is the 01. And then the last bit is turned on, which is 128. FF 01 and then 80, which, if I can get it, 128. So it matches the bits that are up on the screen, except for this example, everything is at 7000 instead of 2000. But the final product, it will be in 2000. So that's how that works. You just basically go across and you turn on different bits. And as you do, you add up the numbers. If they're all on, you get FF. If they're all off, you get 0. So that is how this works. And now we're going to get into some more of the code. Now, I'm going to make a main loop, which is going to be called loop. And in that loop, we're going to JSR to scroll. And then we're going to JSR FFE4 for a little bit of a delay. And branch equal wait. And that will be called wait. And what this is going to do, so it's going to, we're starting a process called loop. This is just a label. It's not machine code. We're going to JSR to a routine called scroll that I have yet to make. And then we're going to JSR FFE4, branch equal, go back up to wait. So this creates a little loop. JSR FFE4 grabs a key from the keyboard, and if no key is pressed, then it returns a 0. So that means it's branch equal. Just think of it like compare number string 0, 0, which I'll just put in. You don't have to, but I will. So get a key, 0 if no key. So that's going to loop, and the purpose of this is just to slow down the scroll for now, just to make it a little bit slower, and then it's going to jump back to loop. So it's going to do the scroll, wait for a key, and then go back and do the scroll again, just so that we don't have it rushing out on the screen. And here is how we're going to break it down. So I've set 0 to column, keeping in mind what I showed you on Ultrafont. The character set is made up of 8 rows and 8 columns. So column is going to be the top to bottom pixels. It's going to be the columns going up and down. Because we're scrolling 8 by 8, we're not going to be scrolling 8 pixels across like that. We're going to be scrolling 8 pixels down. Does that make sense? Let me show you here. So let's say that this is the letter A on the screen in memory. We're not going to be scrolling from left to right like that. We're not going to be putting them on in this order because it's going to be 8 by 8. We only want one column at a time. So we're going to be going like this. We'll be doing the first column vertically, and then the next column vertically, and the next. So that is what column is going to be defining, which column we're on. There will be 8 in total, of course. So we're going to load X with column. And if it's branch not equal, meaning is other than 0, let's just make it easy. Compare X with 0. Branch not equal, next column. So for the first column of every letter, we need to know where to find the information, where to fetch the data for the character. And that is this routine here. So we're going to load Y with 0, and then we're going to load A with BB, comma Y. Remember that BB and BC points to your scroll text. So it's currently sitting on the space. All right. So what it's going to do is it's going to load Y with 0, and it's going to load A with the location where that space is, the first character of TX, because that's what we've set it to. We've pointed BB and BC to go to scroll text. And then we're going to do some math using ASL. So this is times 2, and then times 4, and then times 8. And the purpose of that is it's taking the first, so let me break it down. The first character is a space, and that space is going to be, of course, a 32. 32 is the ASCII, the PETSCII for the space character. So because we have to know where it sits, going back to the ultrafont image, let me just load ultrafont and I'll show you. It's easier sometimes to visualize than to hear me blab about it. All right, so the first character of our scroll text is right here. It's a space. Now, keep in mind this character set is at 7,000, but let's just pretend, all right, let's pretend that right now it's at 2,000, where it's going to be in the final product. Let's just pretend. So we need to know where in this grid to fetch the first character of the scroll. Where in all of this information? So to do that, we have to get the PETSCII value, which is 32. And because every character has 8 rows, we have to multiply by 8. So we're taking space, we're multiplying it by 8, which is going to give us this first row numerically. And then we're going to store it in a location called ADDR low, which is going to be a label. So we're going to put ADDR underscore low equals F9 ADDR underscore HI equals FA. So we're going to be introducing labels instead of 0 page. It might be easier just to use 0 page, but labels kind of make it easier sometimes. So ADDR low and ADDR short for address high. These are your low and high pointer to character set data. So just to go over that, BB and BC are pointing to the actual character in the scroll text. That is what its job is to point you to which letter is going to be displayed. And then address low and address high is to point you on if you refer to ultrafont, to point you to where the data starts for that character of the scroll text. So are we on the first character? Load X with column, compare X to 0. If we're not, we've already fetched the start address, so we're just going to skip it. We're going to go branch not equal next column. Otherwise, we're going to load A with BB, which is the first character of the text, multiply by 8, and store it in address low, which is the low byte of the, well, it's location F9, so it's the low 0 page address. Then we're going to load A with number string 20, because the character set is going to be loaded in at 2000. So at the very bottom of our code, what you're going to do is you're going to put binary, quote, and then 2000 char set, which is the name of the character set we saved from the 99 fonts program. Whatever you called it, you're going to put exclamation mark binary 2000 character set, and above it, you're going to put star equals 2000. If you decide you want to put the character set somewhere else, like 3000, you can change this to a star equals 3000. And then this will be load A with number string 30. So this is probably a little bit confusing. It was a little bit confusing for me too, but again, I'm going to break it down. Let's say your first character is A. So A has a value of 1. All right. So 1 times 2 is 2, times 4 is 4, times 8 is 8. So address low will be 8. And then we're going to take 20, we're going to add 0 to it and put it in high. So address high will be 20. Going back to ultra font, if your character set starts at 2000, and then it goes 2001, 2, 3, 4, 5, 6, 7. 2008 is the very top where the A starts. If we're using the C, well, C is 3, so 3 times 2 is 6, 3 times 4 is 12, 3 times 8 is 24. So it's going to start where the at symbol is, and it's going to go down 24 lines, which is going to bring it to the top of the C. So that's all that this code is doing, is it's taking the letter of whatever character is being printed on the scroll, multiplying it by 8, so it can move over to the correct character set in ultrafont. Well, actually in memory, but just think of it like it was ultrafont. So you'll notice here that we're loading A with 20 and adding 0 to it, and then putting it back into the high address. Why are we doing that? Why are we adding 0? Because what happens is eventually you're going to get into characters for your scroll that you can no longer get to in the first page, in like the 2000 range. It's going to be in the 2100 range. And when that happens, when you multiply it, the excess, the 1, is going to go over into the carry column, just like when you're doing grade 2 math. So it's going to take 20 and add 1, because it's going to be in the carry flag. I'm not going to be able to really explain it to you in a way that you're going to understand it, unfortunately. I can explain the multiply by 8 part so that it goes over to the correct character in ultrafont. But as far as adding 0 to 20, that's a little bit more tricky for me to verbalize. Eventually, you get to a point where the characters, when you multiply them by 8, they're greater than 255. Let's put it that way. Like, for example, let's go into CCS64. And we'll take 42 times 8. So if we want to print the asterisk on the screen, which is the star, well, that's 336. So we can't put a value of 336 into a single location on the 64. So the way that's going to work is we're going to take 42, which is the star, and multiply it by 8. So it's going to get 336. Store in address low. Well, we can't do that, but what we can do is store the 2, so $02, and then the 80. I'm sorry, I'm doing it backwards. We can store the low byte, which is 80, and then the 2 gets carried. So when we load 20 and add 0, it throws in the carry flag, what's in the carry column, and that becomes 22. Does that make sense? I hope so, because I cannot explain it really any other way. So at this point, ADDR low and ADDR high are going to point to the character set information. So we're ready to print it to the screen. And now we're going to do that routine. Now, if we've printed the first column, top to bottom, we already know where the character data is because we've already performed that calculation right here. So that's why I've put load X with column, compare X with 0, branch not equal, next column. We don't need to calculate where the information is in the ultrafont grid every time because we've already done it once. It's in ADDR low and address high. But what we do have to do is we have to display it on the screen. So I'm going to let me just see here. I'm going to choose 0427 as the place to put the text. 0400 is the top left of the screen, of course, and the far right is 0427. Let me just break that down and I'll show you. So if I put a star at 0427, you see a star in the top right. It might be easier, I think, if let's just do this. Let's put screen equals 0400. That will be where you want the scroll text to go. So you can change it, you can adjust it to whatever line of the screen you'd like. So I'm going to change that number less than to screen plus 39. And we're going to store it in FE. And then we're going to load screen plus 39. I'm going to store that in FF. So what that's going to do is it's going to set up another 0-page location, FE and FF, which points to, oh, we have an error. All right, just give me a moment here. So now that we know where to find the information for the character we want to print, we have to break it down into columns. In order to do that, we have to take the character information and AND it with that pixel number to see if that pixel is turned on or off. So to give you an example, let's say that the very first pixel is turned on on the left side, which is 128. So we're going to take what is in the memory address, which would be 128, and we're going to AND it with 128. So what it's saying is if it's 128 in the memory address and in that pixel, then we want to put a block, an A0 character. If it's branch equal, meaning it's not the same, then we're going to skip and we're going to load a space. So I think I'm losing, just on the off chance I'm losing you, I'm going to again load ultrafont. And let's use this example here. So for the letter A, the first column has absolutely nothing turned on. So we're going to take the first line, which is going to have a value of 0. So when it loads address low, it's going to go into this memory address, which will contain a 0. That's 7008. And it's going to AND it with pixel position 128. And that happens to be 1 and then 7 zeros, because the first position is 128. And because it's a 0, well, 1 and 0 are not equal. So that's going to be 0. And means they both have to be the same for it to be a value of 1. And they're different. They're not both turned on. They're not both 1s. So it's going to skip and it's going to put a space. Now, if we say we were to use the B character, but in this example, the B in the first column, these pixels were turned on. So the first column, it's going to have a value of 0. So none of these are going to be lit up. It's going to, because 0, when you AND it with any one of these numbers, they both have to be 1. And they won't be because none of the pixels are turned on. But here, because this is position 128 in bits, it's a 1. It's turned on. So when we load this line of data, and then we AND it with 128, it's going to be a 1, which means it's going to be branch not equal. So then it's going to fall through, and we're going to load A with an A0, which is a solid block because it's turned on. So just to break that down again, we fetched which column our character information is, and then we're loading in the first row, but we have to AND each column, the bits in every column of the first value, to see if they're turned on or not. And we're starting with the first column. So we have to read all 8 rows and see if the first bit is turned on, which is what this routine does. And then what we do is we store Y in 828 just to preserve it because we're using Y already. And then we store the value in FE, which is, of course, the screen location. So it's going to put it in the top right corner. I think I'm failing miserably trying to explain this, but God knows I'm going to try. And then what we want to do is we want to move down to the next row on the screen. So we're going to load FE, which is screen memory, clear carry, add 40 to it, to FE, and store it back in FE, load FF, add 0, and put it back in FF. And the same concept applies with the carry flag. So if it happens to cross over from 0400 to 0500 on the screen, then it's going to have a 1 in the carry flag, and that will get set here. So that moves us down a row. And then we have to do this. So we're going to increment Y, and we're going to compare Y to 8. And if it's not equal, we go back up to extract column. So we're looping from 0 to 7 on the Y-axis, which means we're moving down every line for your character, but we're still only reading the first column because we're ANDing it with pixel position, comma, X, and X is not changing. So it's taking pixel position 80, which is the very first column. And then when we're done, we've done that whole first column. We increment column. I've got a bit of debugging in there to see if we've completed the whole character. Compare it with 8, branch not equal, exit. Exit means we have not finished the whole character yet. If we have finished the whole character, then we reset column back to 0, and we want to move on to the next character. So we're going to increment BB, because BB points to our text. And if it's branch not equal, it rolls over just like an odometer. It goes to exit because it's not equal to 0 yet. And if it is equal to 0, then it's time to increase the high byte. And from there, that's it. But now we have to move on to another routine. And I'm going to put that routine right here. It's going to be called hard scroll. Once we've done the pixels for the first column, we have to move everything over 1. So we're going to use our label that we've set called screen. We're going to load X with 0, create a loop called loop 2, load screen plus 1, comma X, store in screen, comma X, load screen plus 40 plus 1, store in screen plus 40. So remember, screen is the very top left of the screen at 1024. or 0400 in hex. So what we're doing is we're taking position 2. Let me just reset the computer and I'll show you. So the cursor is now on 1024. This is screen, right where the S is. So it's going to load screen +1 and store in screen, comma, X. So it's going to move the D to the left. And it's going to take screen +40, which is the second line, +1, and move that down to screen +40. So it moves the second character in the second row to the first. And we just continue for all 8 lines. Screen +1, +40, 80, 120, 160, 200, 240. Taking the next position over and putting it in the position to the left. Increment X, check to see if X has hit 39. 39 characters across. And branch not equal, go back to loop. And we're going to put that routine, I believe we're going to put that, we have to scroll every line. So JSR, hard scroll. And if this works, I will be amazed. Now, when I press and hold down a key, this is my new 8x8 scroller. There we go. Now, the one thing we haven't done is check to see if it's the end of the scroll yet, if it's wrapped around. And to do that, we have to do that right here, where we load BB, Y, compare number string 00 for the 0 byte. Is it 0 byte? Branch, how should we do this? Branch not equal, not end yet. So it's not at the end of the scroll yet. If it is, then what we need to do is reset the pointer, which is right here. So I'm going to cut this. I'm going to make a routine called JSR reset. Why call the routine? Why make it twice, right? We'll just go reset, and that will reset the pointer. We call it at the start of the code, and then jump fetch. I had the code in the wrong spot. And okay, speed it up. This is my new 8x8 scroller, and it resets. Perfect. Perfect. All right, now, do you think we can make this a smooth scroll? I think with a little work, we can probably implement that. All right, I've made a couple of changes to the code. I didn't put it in an interrupt. What I did was I changed loop. So I load D012 and I compare it to number $30, which is the top of the screen. And if it's branch not equal, loop. So this is going to wait until the scan line is at the top of the screen. And then it's going to take a value of C7, and then it's going to subtract column, where column, of course, we increment from 0 to 7. So that is going to push the screen over 1 pixel for every value for every column that we go over. The screen moves over 1 pixel. And then I'm going to wait for DL12 to reach A0, which is out of the way of the scrolling characters. And then we're going to call scroll, hard scroll, and jump back up to loop. I'm going to show you the final result. It does not look smooth on the video, but that is just because of the frame rate. This is 100% smooth I changed the blocks from solid to checkerboard and implemented a little bit of color. And this is very smooth. It's not running in an interrupt, but you can certainly put it in one. This is the final code. It will be available in the video description. We've set the screen as a label to 0400. Address low and high are the pointer to where to find the character set information. The basic stub, we set the screen color to black. Clear the screen. JSR reset, which initializes the pointer to find the scroll text words. We define the column at 0. And this is new. I'm putting 7 in pixel position because I want to smooth scroll the screen. And this is new code. Load DO12, compare it to 30 hex. If it's not equal, go back up to loop. And that waits for the raster line, the little man that paints the screen, to come back up to the very top of the screen, where we take the pixel position and put it in DO16, which is the smooth scroll register. And what that does is it shifts the screen to the left when we change pixel position, which we do right here. We wait for the scan line to get down to A0 to make sure it's clear of the scroll, because we want to update the characters of the scroll, and we don't want to do it while it's still drawing it. So we decrement the pixel. If it hasn't gone down past 0, it's not time to do anything, so we just jump back up to the loop. Otherwise, we set the pixel position back to 7, and we do these 3 things. We call the hard scroll, which physically moves everything over. We call scroll, which prints the pixels on the far right of the screen, and then we flash some color. So scroll loads the current column. If it is the first column, then we have to get the new information for the character. So we grab the next character of the scroll text. We check to see if it's a 0. If it's not, go down here. If it is, we call the reset routine, and we jump fetch. And fetch just goes right back up and grabs the next character from the beginning of the scroll text. We multiply by 8. We put it in the low address. We put 20 in the high address. And if there's any carryover from the multiplication, it takes effect right here when we add 0. So it always gets the proper page of the character data. And then we put the top right of the screen into FEFF. We set A and Y to 0, and it's time to start checking the column from top to bottom, not left to right. So we check the first address, and we AND it with the pixel 128, which is right here, 80 hex. And if it's branch equal, meaning if it's a 0, so the pixel was not turned on, it goes to skip and loads a blank character. Otherwise, it puts a checkerboard character into A, jumps to plus, where it stores it on the screen, or it will store the space on the screen. Store Y828, load Y828 is just temporarily preserving the contents of Y, because we have to destroy it right here. And then we move FEFF down 1 line so that the next time it draws on the line below. We increment Y. Have we done 8 columns yet? If not, go back up. And then we move over to the next column, top to bottom. Have we done 8? If not, exit. And if we have, reset column and move to the next character of the scroll text by incrementing BB, BC. And then we do a hard scroll, which physically moves everything from right to left. And this is the color routine. Load X with pointer. Pointer is a 0. Load colors, comma X. These are your colors. Byte 614.313.14.0. And then it sets up a loop, stores it in D800, D900. Then we increment the pointer so it moves to the next color next time. Has it reached 6? Because there are only a total of 6. And if not, then exit. Otherwise, reset the pointer so it grabs the first color. And then we're loading the character set in at 2000. Note, this is comma, comma 2, not comma 2, comma 2, as I initially wrote. I made an error. So that will do it. The source code will be provided in the description of the video. And this is Milosov saying thank you so much for your support. The channel is growing tremendously, and I appreciate every one of you. Have a good night.